Hey everyone, and welcome to today's Explainer. Today, we are diving into a seriously fascinating journey. We're going to explore the incredible, completely invisible infrastructure of modern communication. Specifically, we'll be breaking down the core concepts from the Networking Today module. We're going to start at the micro level, just a single computer sitting on a desk, and zoom all the way out to the massive scale of the global internet. Let's find out exactly how the device you're using right now connects to the rest of the world. So here is a question to get us started. How exactly does a message travel across the globe in literal milliseconds? Honestly, it feels like magic, but it is actually highly structured. Think about the Postal Service for a second. If you write a letter to a friend across town or a friend across the entire country, you just drop them both in the exact same mailbox, right? You don't worry about the logistics of it. The Postal Service takes over, they sort your letters, throw them on the right trucks or airplanes, and figure out the absolute best routes to deliver them. Well, computer networks do the exact same thing with your data, just at lightning speed. Today, we are going to look at the post offices, the roads, and the delivery trucks of our digital world. Okay, let's dive into this. Here is our roadmap for today's explainer. First, network components and roles. Second, topologies and network representations. Third, LANs, WANs, and the internet. And finally, building a reliable network. Starting off with Section 1, network components and roles. Basically the building blocks. Think of a networking model kind of like the architectural plans for building a house. Before you can even think about framing the walls or putting on a roof, you absolutely have to understand your raw materials. In networking, these materials are the physical devices and the media that connect them all together. The very first critical component is what we call the host or end device. This is simply a computer on a network where a message either originates from or where it's finally received. Think of the laptop you're working on, the smartphone in your pocket, maybe the smart TV in your living room. Data originates with one end device, flows through the massive infrastructure of the network, and eventually arrives at another end device. They are the absolute starting and ending points for literally all digital conversations. Now, within that world of end devices, we generally have two distinct roles to look at: servers and clients. Servers are exactly what they sound like. They are high-powered computers equipped with specific software meant to provide information. An email server or a web server are great examples of this. Clients, on the other hand, are the devices we use every single day. They run client software, like a web browser or your email app, and they send out requests to those servers to retrieve information. So when you open your browser to check the morning news, your client device is just politely asking a web server to please send over that specific web page. This constant, nonstop cycle of client requests and server responses, that is the actual heartbeat of the modern internet. Okay, but how does that request actually get from your client to that server? Well, that is where intermediary devices step in. We're talking about things like switches, wireless access points, routers, and firewalls. Going back to our earlier analogy, these are the local post offices and sorting centers of our network. And they don't just passively sit there, they actively manage your data. They regenerate and retransmit data signals, they keep detailed maps of what pathways exist, they notify other devices if there's an error, and they figure out the absolute best, most efficient route to get your message exactly where it needs to go. Of course, those intermediary devices need a physical way to pass the messages along, right? And that brings us to the network media. If intermediary devices are the post offices, the network media are the invisible roads carrying those messages. All communication across a network is carried through these mediums. Now, this can be electrical impulses traveling over copper wires, pulses of light bouncing through fiber optic cables, or even invisible electromagnetic waves in wireless transmissions. Moving right along to Section 2, topologies and network representations. It's time to draw the blueprint. Now that we have our raw materials, our hosts, our intermediary devices, and our media, we need a blueprint to understand exactly how all these components physically and logically connect to form a functional structure. Now, what's really interesting about this is the vital distinction between physical and logical layouts. A physical topology diagram is like a literal physical map of a building. It shows you exactly where the wires are plugged in, where the switches sit in the server rack, and how devices are physically cabled together. But a logical topology, that's entirely different. It identifies the virtual connections, showing how data actually flows using things like IP addresses and subnets. So it's actually perfectly possible for a network to look like one thing physically, say a star shape made of cables, but act like a completely different shape logically when the data is actually flowing. Let's look at a super common physical layout for a wide area network, the hub and spoke topology. Notice how multiple remote sites, which are the spokes, all connect back to a single central hub. This is exactly how regional post offices work. They usually don't send mail directly to one another. Instead, they route all of their outgoing mail to a central distribution center, the hub, which then sorts it and sends it out to the proper destination spoke. Now, if we scale up to a much larger enterprise network scale, we get the three-tier enterprise design blueprint. Notice the three distinct layers in this hierarchy. At the very bottom, the access layer provides the actual entry point for users and their end devices. Just above that, the distribution layer acts as a boundary. It aggregates the traffic, handles the complex routing, and enforces security policies. And finally, sitting all the way at the top, the core layer. Its only job is pure, unadulterated speed. It functions as the high-speed backbone to move massive amounts of data as fast as physically possible between different distribution switches. All right, Section 3, LANs, WANs, and the Internet. We are definitely scaling up now. So we've seen how to build the blueprint for a single building or a single enterprise, but what happens when we need to connect whole cities or even countries? To understand to scale this massive, we have to compare a LAN, or local area network, to a WAN, or wide area network. A LAN operates in a very limited geographical area, like a home office or a school campus. It's usually managed by just a single organization, and it offers extremely high-speed bandwidth, mostly because all the cables are short and locally owned. A WAN, however, interconnects those smaller LANs over huge geographical areas, like connecting a branch office in New York directly to a headquarters in London. Because of these vast distances, WANs are actually administered by service providers, and they typically rely on much slower speed links compared to those lightning-fast local LANs. Let's look at how this functions in practice. We basically have these isolated islands of high-speed connectivity: a central office LAN, a branch office LAN, and a home office LAN. The WAN, which is represented by that cloud in the middle, physically ties these separated LANs together. By utilizing telecommunications links, a WAN allows for remote communication so that an employee sitting in their home office can access the central servers just as seamlessly as if they were sitting at a desk in the main building. Now, take that exact concept and multiply it by millions, and you get this: the Internet. Literally, it is simply a worldwide collection of interconnected LANs and WANs. You've got hospital LANs, government LANs, school LANs, and home LANs, all tied together by an incredibly complex global web of wide area networks utilizing copper, fiber optics, and wireless links. It is a network of networks, allowing your specific device to talk to practically any other device on the planet. Which brings us to our final part, Section 4, building a reliable network, passing the inspection. But here's the catch. Just plugging cables together doesn't mean the network will actually work well when thousands of people try to use it all at once. Much like a newly built house has to pass an inspection to ensure the roof isn't going to cave in under heavy snow, a network must be designed from the ground up to withstand failures, heavy traffic, and future growth. To guarantee this reliability, architects focus on 4 fundamental pillars: fault tolerance, scalability, quality of service, and security. And trust me, if any one of these 4 pillars is weak, the entire network experience suffers. So the absolutely crucial point here is understanding how each of these pillars functions. Fault tolerance means building in redundancy, like having duplicate routers or extra cable links, so that if one device completely fails, the network instantly routes around the problem without the user ever even noticing. Scalability means the network can easily grow and accept new users without degrading the performance for the people already on it. Quality of service, or QoS, is all about prioritizing critical traffic, making sure your live video call gets priority over someone else downloading a massive non-urgent file in the background. And finally, security ensures that the data flowing across all these invisible roads is heavily protected from unauthorized access or malicious damage. Now, to guarantee these 4 pillars actually hold up on a global scale, engineers rely on strict models. Like we said, think of a networking model as an architectural blueprint for building a house. Today, the world relies almost entirely on the TCP/IP networking model. Because every single vendor out there, whether they make the smartphone in your hand, the router in your living room, or the massive server sitting at Google, follows this exact same TCP/IP blueprint, all of their equipment can speak the exact same language seamlessly. So, we have covered the journey from your personal laptop all the way out to the vast global web of the Internet. We've examined the physical hardware, the topology blueprints, and the architectural pillars that keep it all running smoothly. But it leaves us with a pretty intriguing thought. Your devices are connected, they have their physical roads, but do you know the exact rules they're forced to obey every single time they send a packet of data? The hardware is really just the beginning. The real magic lies in the protocols that govern them. Thank you so much for joining me on this explainer, and remember to keep questioning how the invisible world around you really works.